Right, so we've made sure we've got the correct paper. You've put your name on it. Okay, that it's a foundation paper and that it is, we've got specimen 18 set 2. Okay, if you'd like to open the paper, you do need to be in total silence. So question 1, it says this question is about structure and bonding. Figure 1 shows part of one layer of graphene. Which element is graphene made from? Okay, so this is an AO1 question. In other words, it means that you have to, it's one of those recall questions. You either you know it or don't. However, there are clues for it later on when we look through the paper. So you could always come back to this. When it's going to be carbon. So you're going to make sure you put a clear tick in there. Can you also, yes, you're filling in your paper now. Can you also, if you weren't sure and you think you might want to change your mind, do it in pencil. Okay, you can tick that in pencil and come back at the end. There will be time. Okay, so that was question 1.1. Over the page, question 1.2. If you find it, please. It says each atom in graphene has one delocalized electron. Complete the sentence. Choose the answer from the box. So we need to know what delocalized means. Now, the word delocalized we understand as being not held in one specific position. So is that going to help it act as a lubricant, to be used as a fuel, conduct electricity, or dissolve in water? So delocalized electrons allow graphene to conduct electricity. Shh. You can write that in. I'm not asking you to answer any of these questions out loud. When you have over the page, please. So 1.3, it says which structure is a fullerene? Okay, now we've got one here with carbon atoms, one with oxygen and hydrogen, one with oxide and magnesium, and one with carbon. So that would lead me to believe, even if I hadn't got a clue, that would lead me to believe that it's the ones with the carbon atoms that we are interested in. Yeah, so I can discount the middle two. So it's either the top one or the bottom one. So the top one is a diamond structure. It's got 4 bonds around every carbon. We've got 1, 2, 3, 4 bonds around every carbon, whereas the bottom structure only has 1, 2, 3 bonds. Our fullerenes can conduct electricity, so it's going to be this bottom diagram. Okay, so it's the bottom one, that is a carbon nanotube. Over the page. So figure 2 shows part of a large hydrocarbon molecule. Which 2 elements are in all hydrocarbons? Hydrogen and carbon. I'll give you some nice easy ones to get you started. If you found that when you started, if you found that the first question was too difficult or was asking you something you don't get thrown by it, literally move on to the next part. So 1.5, it says complete the sentence, choose the answer from the box below. So a large molecule represented in figure 2 is either an atom, a metal, a polymer, or a salt. Right, well, we know it can't be an atom because we've got 2 elements in there. So it can't be the first one. So I'll cross that one off my list. It's not going to be a metal because it's got carbon and hydrogen. Now those are non-metals, so I can cross that one off my list. So it's either going to be a polymer or a salt. Now, poly means many. And so this is a polymer. It's saying with that N at the end after the brackets, the N means it's a repeated, that's a monomer, that's a one unit, and it's repeated a lot of times. So it's going to be a polymer. Shh. Next one, 1.6, we're completing the sentence. So it says, so choose an answer from the box. It says metals can be stretched into wires because the layers of the atoms can, well, it's not going to be attracting because that's not going to help it stretch, is it? That's going to be pulling stuff together. Bonding's all about tying stuff together as well. We've either got slide or vibrate. If we want something to stretch, we probably want it to be able to slide. So our answer is slide. Shh. Over the page, please, for question 2. So this question is about electrolysis, and I know many of you struggle with this particular concept. So, however, the first few parts of this question are not complicated. They don't require much knowledge in the way of electrolysis. So it says, how many different elements are in the formula AgNO3? Well, we've got an Ag, we've got an N, and we've got an O3. So that's 3 different elements. How many atoms are in the formula? So we've got one Ag, which is silver, 1 nitrogen, and then 1, 2, 3 oxygen. So in total, I've got 1, 2, 3, 4, 5 lines. So it's going to be that third box, 5. Over the page, and we've got a diagram of electrolysis. It says an electric current is passed through silver nitrate solution, and this shows the apparatus. The solution contains 4 ions, so Ag plus, H plus, NO3 minus, 3,1 minus, and OH minus. Okay, so it's our solution here. So it's this bit. It says, where do the H plus and OH minus come from? Ions come from? Well, they're not going to come from the air. They're not coming from the electrodes. They could come from the silver nitrate, but that's only got silver and nitrate in it. So it's going to be coming from the water. So it's going to be the bottom box. They're coming from the water because water splits into H plus and OH minus. Okay, over the page, please. And we're looking at question 2.4. Okay. So we've got Ag plus ions and H plus ions, and they're attracted to the negative electrode. Give the reason why. Okay, so I've got a positive ion there and a positive ion there, and they're being attracted to the negative electrode. Why would that be? It's going to be because opposite charges attract. Okay. Oops. Shouldn't be writing outside the lines. The reason they have the box lines here is that these pages, when they get taken, when these exam papers are sent off to the exam board, they get cut down the side there to separate them, and then they get sent out to different people to mark different. They get scanned and sent out electronically. So you always write inside the line because that might not scan anything out here. Oops. anything out here might not scan properly. Okay, so question 2.5. It says silver is produced at the negative electrode and not hydrogen. What does this tell you about the reactivity of silver? Well, we've got 4 statements. Silver is less reactive than hydrogen. Well, that was a possible. Silver is less reactive than oxygen. That's not talking about hydrogen, is it? So we don't want that. Silver is more reactive than nitrate. Again, that's not talking about hydrogen. And silver is more reactive than water. No? So it's going to be our top box. It's less reactive than hydrogen. Okay. 2.6. The hydroxide ion, OH minus, is attracted to the positive electrode anode. The equation shows what happens at the positive electrode. Name the gas produced at the positive electrode. So we're talking about products. So which one in here is a product that's gas? Well, we've got water, oxygen, and some electrons. So it's going to be our oxygen. That is our gas. Okay, over the page. Okay. An electric current is passed through sodium chloride solution. Now, we've got a lot of information here. Okay, but what I would say to you, when you have a big question like that, read with purpose. So have a look at the bottom part. It's always just before the actual mark is the question itself. It says give the name of an indicator and give the color of the indicator in sodium hydroxide solution. So it may not even be necessary to read through the whole of this question. So it says after passing electric current through the sodium chloride, one product, sodium hydroxide, is in solution. The presence of sodium hydroxide can be shown by adding an indicator. So what indicator might we want to show, want to use? We could use universal indicators. There are lots of different indicators. In this case, we're going to use universal. And there are different ones. You've got phenolphthalein, you've got litmus, you've got methyl orange, you've got all sorts of different ones, but in this case we'll use universal. And what color? Now, sodium hydroxide. Hydroxide means it's going to be an alkali. So its color is either going to be blue or purple. Okay, so universal indicator will go blue or purple in the presence of an alkali. Okay, over the page, or over 2 pages, because we're on to question 3 now. So this question is about compounds of fluorine. So fluorine has a fluorine atom has 7 electrons in its outer shell. Figure 5 shows part of a dot and cross diagram of a molecule of hydrogen fluoride. Complete the dot and cross diagram in figure 5. You should show only the electrons in the outer shell. Okay, we've got 1 electron already shown as a dot, and that is on that from that hydrogen. So our first mark, we've got to put 7 in this outer shell. First one is going to go to form that covalent bonding pair. So the first one goes inside that sort of that intersection, as if these are like Venn diagrams. And that gets us our first mark. And then the other 6 from our 7 are going to be distributed around the outer shell. What I would say is draw them in pairs, then you don't lose track of how many there are. So we've got 1, 2, 3, 4, 5, 6, 7 that I've put in there, and would be getting 2 marks for that. At the bottom of the page, we've got a figure that is going to show us, that's showing the boiling point and melting point of oxygen difluoride. We're going to need that information in a minute. Let's look at the next question. So question 3.2. What is the state of oxygen difluoride at minus 200 degrees centigrade? Okay, so we're going to need to look at that figure 6. So we've got boiling point at minus 145. So everything to the right of that is going to be a gas. We know that the melting point of minus 124, everything to the left of that has got to be a solid. So everything in the middle has got to be a liquid. So if we go back to our original question, and it says, what state of oxygen difluoride at minus 200 degrees centigrade? Well, we know that it can't be a solid, because that was, we're looking at 200 degrees, which is going to be somewhere in the middle here. Yes, so that's our 200 degrees. It's going to be in that central zone. So it can't be a solid, it can't be a gas. We're left with aqueous or liquid. Now, aqueous means it's in solution. There's nothing else going, nobody's said anything about a solution here. So it must be, it's going to be a liquid. Now it says, what change of state occurs when oxygen difluoride is cooled from 220 degrees, minus 220, to minus 230? Let's double check our diagram here. Yes, minus 224 is the melting point. So if we're going that way down the scale, it's going to end up turning into a solid, which means it's not condensing, because that's a gas to a liquid. It's not evaporating, liquid to gas. It's going to be freezing, not melting, because it's not going from solid to liquid. Over the page, and now we get some longer answer questions. Okay. Potassium reacts with fluorine to produce an ionic compound called potassium fluoride, KF. Figure 7 shows the transfer of electrons during the reaction. Okay, so the question is asking me to describe what happens when potassium reacts with fluorine to produce potassium fluoride. Write about electron transfer. Okay, it's asking me to describe something. So it's asking me to describe the differences between that, our reactants, as it were, and that, our products. So it's making observational comments for a description. So the things that I'm going to think about then, what are the differences between the two diagrams? Okay, well, I can see the potassium, the K, has lost an electron from its outer shell and become an ion with a positive charge, and that fluorine has become a fluoride ion with a negative charge because it's gained an electron in its outer shell. So we're looking for 5 marks here. So the first mark I would suggest is the fact that the potassium loses an electron. And forms a positive ion. You could probably say it gains a positive charge, or now has a positive charge. And what's happening to the fluorine? The fluorine is going to gain an electron to form a negative ion. I've literally written 2 sentences, and that has given me that's given me all 5 marks. I've identified that the potassium is losing, and it's 1 electron. So I've used that by using the singular, an electron. You could put 1 electron, yeah, and it's forming a positively charged ion, yeah. The fluorine gains 1 electron, and it is forming a negative ion. Okay, that gives us all 5 marks. Don't be daunted when you see a big space to write in. It could be that you don't have to write that much. I know some of you think we'll sort of look at a big space like that and think, I've got to fill it up. You don't. So the same with the over the page. So 3.5. Again, you've got a large space. You do not need to complete all of those lines. Okay, it's a 4-mark question. So this time, potassium fluoride is an ionic compound. Explain why ionic compounds have high melting points. Use the following words in your answer: attraction, energy, and ions. Okay. So the first thing it said is to identify what type of answer I'm going to give. So it's going to be an explain why. So I've got to give reasons for everything. So I would probably start this off by with a complete sentence. So how would I start an ordinary sentence off? I would probably start this off by going, ionic compounds have high melting points because. Yeah. So ionic compounds have high melting points because. Now, if you want, you can. I'll give you time to write this down in a moment. If you want to watch and listen, and then I'll give you some time in a minute to write it down. Okay, so ionic compounds have high melting points because. Now we've got 3 words there we need to include. So if it's got a high melting point, then we're talking about strong forces of attraction. Okay, so I've got because it has strong forces of attraction, so I've used that word. Between ions. Okay, I've been specific. So strong forces of attraction between ions. Okay, this means I need to use the word energy in my answer. So this means it requires a lot of energy to break those bonds. Okay, so I've said it. I've used the 3 words, but it's asked me for 4 marks. So there must be something else I can say to get that 4th mark. So I could make a comment about the structure. You could make a comment to say something along the lines, because ionic compounds form giant lattice structures. So I've used a comment about attraction, I've used a comment ions, and I've used the word energy. And then my fourth mark is saying these compounds form giant structures. So can you get that answer written into your booklet? Remember, you will be doing this exam tomorrow. Not tomorrow, Thursday morning. Okay, over the page. You're not finished? Okay. It's fine. We've got plenty of time. Okay. Are we ready now? So let's move over to question 4. This is already halfway through the paper. And this is the last of the lower ability questions. The first half of the paper have all been low demand questions. This is the last of the low demand questions before we move on to the standard demands, which are the ones that are found on higher tier as well. Okay, so question 4. It says this question is about compounds of oxygen. The reaction between carbon and oxygen is exothermic. What does exothermic mean? Even if you couldn't remember, you can work it out with a lot of keywords. You can work them out. So exo means to give out something, exit, and thermic is to do with heat. So exothermic reactions are going to give out thermal energy to their surroundings. Okay, so they're going to transfer heat energy to their surroundings. Okay. Okay. Question 4.2. We've got 3 diagrams. Let's squish that up a little bit. It says, which is the correct reaction profile or energy level diagram for an exothermic reaction? Now we've said, so on the axis, it's got energy increasing as you go up that y-axis. So if it's going to give out energy to its surroundings, then our products need to be at a lower energy level than the reactants. Our reactants are where they start, our products are where they finish. The first one, we've got reactants as more energetic than products. The second one, reactants have less energy than the products, so we'd have to put energy in. And the third one, they are their level. So we know we can't be the third one. This one looks like it's climbing a hill to get up there. This one looks like it's rolling down this hill. This is the one that's going to be giving out energy. So it's the first box. Okay, over the page. So 4.3 we're looking at. What's the matter? Right, 4.3. We have a maths question. Maths questions are your friend. Oh, they are. Generally, a lot of the maths questions require very little in the way of scientific knowledge. They just need you to be able to plug numbers into an equation. And with the chemistry, they're not asking you to remember an equation. Look, they gave you the equation. So you are just going to put some numbers in there. It says the percentage by mass of oxygen in carbon dioxide is calculated by the equation percentage by mass. So number of atoms of oxygen times relative atomic mass of oxygen times 100, and all divided by relative molecular mass of carbon dioxide. Okay. So in other words, how much oxygen is in carbon dioxide? So calculate. So we're going to plug some numbers in. So how many atoms? So I've got CO2. That's my compound. How much oxygen is there in the CO2? Okay, so using my equation, it says number of atoms of oxygen. So how many have I got of those? I've got 2 of those. 2 times, and it says relative atomic mass of oxygen. Well, it's given me, I don't even have to look at the periodic table for that. It gave me the relative atomic mass of oxygen. So 2 times 16 times 100, because that's what it said. So 2 times 16 times 100 divided by, and it says relative molecular mass of carbon dioxide. So in other words, how much does carbon dioxide actually weigh? Well, we've got 1 carbon, which is 12, and 2 oxygen. So 12 plus 16 plus 16. So that's the mass of carbon dioxide, isn't it? 12 plus 16 plus 16. And that's going to give us, it's going to give us 72.7%. Actually, it's going to give us 72.7272727272. They will expect me to round this, but they haven't been specific as to what to round it to. So I would just do to 1 decimal place. Okay, so we've got 72 point. Now there are 3 marks available for this. 1 mark is available for working out carbon dioxide. 1 mark is available for writing out that whole sum and proving that you know how to do it. And 1 mark is for actually getting the right answer. Okay, this is what I mean. Maths questions are your friend. Even if you haven't got a calculator, you could get 2 out of those 3 marks. Okay, over the page, it says balance the chemical equation. Now, I know some of you struggle with balancing equations. It is a 1 mark question. If you genuinely struggle with this, do not fret. But it is, because it is only a 1 mark question, but we're trying to get every single mark that we can. So I'm using my pencil. Because what I need to, because it means if I make a mistake, I can rub it out. Mitchell. So balance the chemical equation. Okay, I've got 2 hydrogens here. And I've got 2 hydrogens there. Lovely. We need to have the same number of each atom on either side of the equation. Done. I've got 2 oxygens there, but I've got 1 oxygen and 1 oxygen. So I've got and 2 oxygens. So I've got 3 oxygens on this side of the equation. Okay? Because I've got 3 oxygens and only 2 there, I'm going to have to multiply by 2, aren't I? So if I double that, I've now got 4 hydrogens, 2 oxygens and 2 oxygens. So that's 4 oxygens. On this side, if I'm going to need 4 hydrogens, I'm going to need to double this one as well. So I've got 4 hydrogens and 4 oxygens. Okay, So I've just put a 2 and a 2 in there to balance that equation. If it helps you when you do these, when you do this one, you could always draw out the atoms themselves. So I'm saying, okay, I've got 2 hydrogen, I've got 2 oxygen, 2 hydrogen, 1 oxygen, and so I can see that I've got 3 of them there. What could I do? Well, if I double them, that gives me 2. So I've now got 1, 2, 3, 4, 5, 6. Oh, I'm not doubling this one, am I? I'm only doubling the other one. So 1, 2, 3, 4. And then if I double this, that means I'm going to double these. 1, 2, 3, 4. Okay. So question 4.5. Okay, it says 6.8 grams of hydrogen peroxide decomposes, so breaks apart, to produce 3.6 grams of water. Calculate the mass of oxygen produced when 68 grams of hydrogen peroxide decomposes. Right, it's 2 marks. So, first of all, I'm going to look at the relationship. Now, the mass on this side of the equation is going to be 6.8 grams plus, now I've got the mass of water, which is going to make 3.6 grams plus whatever the mass of oxygen is. Now I know this together must weigh 6.8 grams. So the difference between the two is going to be the mass of my oxygen. So I've got 6.8 minus 3.6 is going to give us 3.2. So I've got 3.2 grams of oxygen. But in the question, it says calculate the mass of oxygen produced when 68 grams of hydrogen peroxide decomposes. So I need to recognize that 6.8 times 10 equals 68. Therefore, 3.2 is going to make 32 grams. So I want 32 as my answer. So I've got 1 mark for working out the 3.2, and I've got 1 mark for multiplying by 10. Okay. Over the page. Oops. Can I leave it there for a second? Of course. Here we go. So 1 mark for calculating that it's 3.2, which is that sum there. So 6.8 minus 3.6 will give us 3.2. And then 1 mark for recognizing that I've scaled this up by a factor of 10. Are we okay now, James? Okay, no worries. Okay, over the page then, and we're going to look at question 5 now. Okay, this is about the periodic table. So first, now these are the start of the standard demand questions. So these are the questions that we might find on the higher tier paper as well as the foundation tier paper. Right, It says compare. So it says this question is about atoms and chemical elements. Mendeleev's periodic table has groups of elements with similar properties. It says compare Mendeleev's periodic table with a modern periodic table. So you're going to need to use your modern periodic table. And it says which group is missing from Mendeleev's. Okay, well, on my modern periodic table, I've got 1, 2, 3, 4, 5, 6, 7 and group 0, whereas on Mendeleev's one I've got 1, 2, 3, 4, 5, 6, 7, and actually there's nothing in here for group 0. So I've definitely got a 1, I've definitely got a group 2, definitely got a group 3, definitely got group 7, missing some group 0. So that's the one I'm going to choose, is the bottom one. So group 0. Okay, over the page. We're just going to wait a minute. Have a look at that question. See what answer you come up with. Just going to wait a minute while. So, in the early periodic table, some elements were placed in the wrong groups. Mendeleev overcame some of these problems in his periodic table. Give 2 ways he did this. Well, even if we look at that first version of the periodic table that we've got here, this is Mendeleev's one, we can see there's a missing element. So one way was he was able to leave gaps. So he recognized the fact it was okay to leave some spaces. All right. So our first part of that answer, so one way would be leaving gaps. And then secondly, if we look at that periodic table, everything is in mass order. Okay, so he has put everything in mass order. All right, so he changed the order based on their weights. Okay, so if we can fill in those, please. Okay, right, 5.3. So it says, draw one line from each scientist to the discovery that the scientist made. So Niels Bohr, he either discovered electrons, he discovered that the electrons orbit the nucleus, the existence of neutrons, mass of the atom was concentrated in the center, and the protons were found in the nucleus. Okay, now Bohr was the Bohr model is the one with all the circles around the outside with the electron shells. So he has to be the guy that worked out the electrons orbit the nucleus. You need to do these lines so that they go both boxes. It's better that they go into both boxes. And secondly, it's also, can you use a ruler? If you are not sure, again, draw them in pencil first. You can always go back over them. Chadwick was the one that came up with the discovery of the existence of neutrons. So Chadwick was neutrons. So we've got Bar for electrons, and Chadwick is neutrons. Okay, over the page again. Continuing with question 5. Right. So, question 5, it says a beam of electrons, neutrons and protons can be separated by passing them through an electric field. Figure 9 shows the directions of the 3 particles after entering the electric field, and then it makes a comment to say that charged particles are attracted to the oppositely charged plate from the electric field. So if I look at that diagram, particle A, this first one, has been attracted towards the positive plate, so it must mean that it has a negative charge. The bottom one has been attracted towards the negative plate, so it must mean that it has a positive charge, and the third one has to have no charge because it was unaffected by the positives or negatives. So when I look further down, it says which direction A, B or C does each particle follow. So an electron, we know, has a negative charge, so it must be direction A, because that's the direction that had the negative charge on it. Neutrons must be direction B, because that has continued on in a straight line. That's the neutrally charged direction. And then protons must be direction C, because that was our positively charged direction, wasn't it? Because that was the one that was attracted to the negative plate. So you should have A, B and C worked out. Can you move those 2 tables apart, please? Okay. Over the page, we're doing 5.5. It says calculate the mass of 1 atom of sodium. Use the equation. So again, it has given us the equation. Maths is our friend. We just fill in some numbers. So 1 mass of sodium. So that's the bit we're trying to find. And it says relative atomic mass divided by something called Avogadro's constant. And spookily enough, they've given us Avogadro's constant. And then it says give your answer to 2 significant figures. All right. So let's put some numbers into that. So the relative atomic mass of sodium, we look at our periodic table, we find sodium on our periodic table. Relative atomic mass of sodium, it's going to be 23. It's the bigger number, it's the more massive number is our mass. Okay, so we've used the periodic table to say 23. Now it's going to be, so that our relative atomic mass divided by Avogadro's constant, which they've given us. So that is 6.02 times 10 to the 23. Okay, so just putting in those numbers gives us a mark. If we then put the answer, which would be 3.8, and then it comes to a whole litany of numbers times 10 to the minus 23, that would only give us, if it was like 8, 1, 5, 6, 7 or whatever, it would only give us 2 marks because we've not rounded it down to 2 significant figures. That's our third mark, is to give us the 2 significant figures. 3.8 times 10 to the minus 23. So by losing that bit, that gains us our extra mark. All right. Are we okay with that one? Okay, next one. Again, mathematics is our friend. It is. Pardon? 3.8 times 10 to the minus 23. Maths is your friend. Okay. Again, on the face of this one, this next question looks quite challenging, but actually, once we break it down, it should be absolutely fine. So first of all, so it says the radius of a sodium atom is 227 picometers. 1 picometer is 10 to the minus 12 meters. And then the radius of a nucleus is 1 over 10,000 of that atom. Okay, so it's given us 3 pieces of information there. 227 picometers. It's told us that a picometer is 10 to the minus 12. And then it says the radius of the nucleus inside of that atom is a ratio of a fraction of 1 to 1 over 10,000. So 1/10,000th of the diameter of the radius of that atom is going to be the radius of the nucleus. Okay, right, so let's have a look at the alternatives they've given us. They haven't asked you to calculate anything. They're just saying which of these alternatives will give us which calculation shows the radius of a sodium atom's nucleus. So how are we going to combine those 3 bits of information to correctly find us the answer? Okay, so the first one, it's got 227 times 10,000. Well, for a start, that's missed out anything to do with a picometer, and we know we're talking picometer, so it cannot be that one. Next one's more plausible. You've got 227 times the fraction. But again, there's nothing about 10 to the minus 12. So that's not plausible. The third one, this is looking better. We've got 227 times 10 to the minus 12, so that's better. But then it's times 10,000. Now, we know from this that third bit of information that it is 1/10,000th, a fraction of it. So it cannot be the third one. So by a process of deduction, it must be that bottom option. So a clear tick in that box. Right, over the page, and we're going to look at question 6. So, some students investigated the change in temperature as sodium hydroxide solution is added to dilute sulfuric acid. And then I can see it has given me a method. I am not going to waste my time reading the method yet because I don't know what it wants me to do with it. It's given me it for a reason, but I don't know what the reason is. So I'm going to go and look at the question on the next page to see what information it's going to ask from me. So it says the volume of sodium hydroxide solution is a variable. Which 2 words can be used to describe this type of variable? Okay, so I'm going to need to know how that sodium hydroxide is being used to be able to answer this. Okay, so I'm going to go back to my method now. And we're looking for sodium hydroxide. So step 1, put 25 centimeter cubed of dilute sulfuric acid into polystyrene cup. Well, that's got nothing to do with it, so ignore that one. Measure the initial temperature. That's got nothing to do with sodium hydroxide either. Add 4 centimeters cubed of sodium hydroxide solution to the dilute sulfuric acid. So that's interesting. It's saying I'm adding some sodium hydroxide. Stir the mixture. Not bothered. Measure the highest temperature. Well, I'm not measuring it, so that's giving me a clue. So it's not the thing that I'm measuring. So which variable might it be? and then it repeats steps at 3 to 5 until 40 centimeters has been added. Okay, so those are the two that it's been mentioned in, and it's definitely not measuring anything. So let's have a look at my options. So we've got categoric, continuous, control, dependent, and independent. Okay, so it's our control, dependent, and independent we're looking at. Now, control means we keep it the same each time, and we don't, because we've changed it by 4 centimeter cubed each time, so it can't be that one. Dependent is the thing that we measure, and we're not measuring that as a consequence of the experiment, so it has to be our independent variable. It's the thing we are choosing to change. But it's asked me for 2 boxes, which 2 words. So it's asking me about categoric and continuous data. Categoric is when it's different types of things. So that could be bananas versus oranges versus potatoes. Whereas a continuous is something like time or temperature. Now we're talking about we're going to be talking about a volume of a liquid, so that is our continuous variable. Okay, so those are the 2 that we've ticked off that box, off that question. Over the page, and we are looking at 6.2. Dylan, desk down, please. Okay, dilute sulfuric acid has an initial temperature of, and it says 24 degrees centigrade. Figure 11 shows the highest temperature, and calculate the temperature change. Okay, so we need to double check that we've got the scale correct, so that each one of these marks on the scale is going to be, it counts for 1, not 2. Okay, and we've got it just over, part way between the first and the second, so that's going to be 31.5. Now we're going to need to subtract those 2, aren't we? So 31.5, subtract, take away 24 is going to give us 7.5 degrees centigrade. So into the box, we've got 7.5 degrees centigrade. Okay, so the difference between those 2 numbers. We've got a graph at the bottom of for figure 12. Graphs are our friends. We shall be using that in a moment. So it says over the page 6.3, and we've got determine the volume of sodium hydroxide solution that gives the highest temperature change. So I want highest temperature change. I'm going to go look at my graph and look for the highest temperature change. Well, that's on this axis. So I'm going to get my ruler, and I am going to draw a line. Now that's the highest temperature change, but what did it ask me again? It's the volume of sodium hydroxide to give the highest temperature change. So my highest temperature change, we can see there, is peaking up here, but I need to trace it down to that x-axis to find the volume. Okay, which if we count across is going to be 26 centimeters cubed. So 26 centimeters cubed. Okay. As I said before, when you have a graph in there, it is a question that you can almost guarantee to be able to get marks on, because you all know how to deal with graphs, regardless of whatever the content was about. Okay, figure 12 has in figure 12, the temperature when 16 centimeters cubed of sodium hydroxide solution was added is anomalous. We do need to know what the word anomalous means, that it doesn't fit the pattern. Suggest one error that could have been made in the method which would cause the anomalous result. Okay, if we look back at the method quickly, look at the steps involved. Now, this is the important bit where we're adding stuff together. Where could we have made a mistake in there? Well, there's possibility something to do with stirring or measuring the highest temperature. So either one of those is a suitable alternative or suggestion for that as an answer to that. So it could be not measuring the temperature correctly. So you didn't stir it, maybe. So didn't stir. Or you could add, it's only one mark. You only need to put one answer. So you didn't stir it. It's perfectly acceptable. Or it just didn't wait for the highest temperature to be reached. Okay. Right. 6.5. Sodium hydroxide solution in this investigation contains 80 grams per dm cubed. The students use 40 cm cubed units. Be careful with units of sodium hydroxide solution. Calculate the mass of sodium hydroxide in 40 cm cubed. Okay, how are we going to do this? Well, we need to make sure that we've got the same units. So how many cm cubed are in a dm cubed? Well, if we think about it, a dm cubed is a litre, which is, if we measured it out in a square, would be 10 centimetres times 10 centimetres times 10. I'm not using that in my answer, okay? If that makes you feel better, 10 times 10 times 10, okay? Which is 1,000. So I've got a ratio. So I've got 80 grams, and it's dissolved in 1,000 centimetre cubed of solvent. But I want to know how much is in 40 centimetre cubed of solvent. So for my first marking point, I've got 80 divided by 1,000. That's showing me what my initial concentration is. And then multiply by 40 to say, well, I only actually want to know what's in 40 grams of it. So what is 40 centimetre cubed of it? So in my 40 centimetre cubed of this. Okay, so you get your first mark for getting that bit. Your second mark is going to be the fact that you've done this times by 40 because you've recognised that that's how we're going to find our information. And then finally, you're going to write 3.2 as an answer on that answer line. When it says per in the question, anything that's, so miles per hour, it means divided by. Remember, okay? So per in the question means divided by. Just give you a minute to write that down. Mitchell, don't throw it around, please. Okay, over the page. Question 7. So this is the final question on the paper, and therefore it is the most difficult question on the paper. So first things first. It says, so we're talking about metals and metal compounds. Copper oxide reacts with hydrochloric acid to produce copper chloride and water. Copper oxide is insoluble in water. Copper oxide is gradually added to hydrochloric acid until it's in excess. Sketch a graph on figure 13, so using these axes at the bottom of the page, to show how the pH of the hydrochloric acid would change. Okay, so to start off with, we've got copper oxide reacting with hydrochloric acid to produce, that's our reaction, and the copper oxide is gradually added to the acid. So we know the pH at the bottom, where it intersects this axis, has got to be somewhere in this bottom region. Okay, you can go as low as 0, anywhere in there. Okay, but this is a sketch. Okay, so we know it's going to be going, and it's going to be increasing because we've got a neutralization reaction occurring here. Now, the important bit is the fact it says it's insoluble in water and that we're adding it to excess. Okay, so if we're adding it to excess, it means that there will be no more acid left because we've added more of that base than there is acid. So we know that it will get to the point where there's no more acid, but it says it's insoluble in water, which means it's not an alkali. It will not pick up a pH above that of water, and we know what the pH of water is. It's 7. So when it comes to sketching my graph, you can do this freehand or you can use a ruler. We know that the final line cannot go above 7. Yeah, but we also know that this is going to increase until it gets to 7. So you can draw it with a ruler like that, or you can draw it freehand and put a curve in there. Either way, they want to see that the pH doesn't go above 7 because it's not an alkali. But that we start with the pH below 7. Okay. So that's our sketch graph. Over the page. This is our big 6-mark question. You knew there was one on here somewhere and we finally found it. So it says magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen. Plan an investigation to find the accurate volume of hydrogen produced from magnesium. So I need to find an accurate volume of hydrogen, and I need to react magnesium and hydrochloric acid. Okay. But I don't need to think about safety, so no mention of safety specs or anything like that. I don't need to worry about that. Okay. So what I would do if I was doing this first is I'm going to think to myself, what equipment am I going to need to use? This is one of our required practicals. What equipment am I going to need to use to find an accurate volume of hydrogen? So I'm going to draw a diagram. So the first, and I can get marks from my diagram. So I'm going to use maybe a gas syringe or something similar. So I'm going to have a flask in which to place my 2 reactants. So I can get, as I said, I can get probably half of the marks on this without doing anything other than drawing a diagram. I don't have to write sentences or anything, but that's where I'm going to get my extra marks. So first of all, I'm going to draw, and it's not Picasso. It is a question of you draw a flask, a sidearm flask, with a bung in it. Can you just watch for the moment? You get to draw this in a minute. I've got a delivery hose, and then I'm going to use a gas syringe because that's going to be my most accurate way of collecting that gas. Okay. In there, I'm going to end up with my magnesium, and I'm going to put my acid. That's not going to get me any marks, but if I label it, it will. So I'm going to label in my gas syringe. I'm going to label a conical flask. I'm going to label magnesium. I'm going to label acid, hydrochloric acid. I'm going to label a bung. I'm going to label a delivery hose. And I'm going to label So actually that is my gas syringe, and in there is my hydrogen gas. Okay, that's certainly going to get me 2 marks. It might even get me 3. If I want to ensure that it gets me at least 3 and maybe 4, I'm going to put some quantities. So if I put hydrochloric acid, so if I have a dilute, sorry, D-I-L-U-T-E, dilute hydrochloric acid, and I just put 25 cm cubed there, that shows I've got a repeat, I've measured something out. Magnesium, if I put 1 gram, it shows I've measured something, or 3 centimeters, I've measured something. So that if somebody wanted to repeat my experiment, it would be reproducible. They could repeat it exactly the same and get the same answer. Okay, then I'm going to put, so that's probably going to get me at least 3 out of my 6 marks, just that diagram. Then I'm going to provide a method to explain what's going on. I'm going to give you some time in a minute to do the drawings and stuff. Okay, so if I've drawn a diagram, that's saved me having to explain how to set this up. So it's like, set up the equipment in the diagram. That's the whole point of doing the diagram, isn't it? So set up equipment as diagram. Then I'm going to tell them about measuring. So I'm going to put measure 25 cm cubed of dilute HCl, that's hydrochloric acid. Now I've used the word dilute. I could be more specific and give an actual molarity, so 1 molar, or so how concentrated that acid is, but it will be sufficient to just write dilute hydrochloric acid. But you could give a specific molarity because it is important that we know the concentration of that acid. So how am I going to measure it? I'm going to measure it in a measuring cylinder. And transfer to flask. Okay. What am I going to do next? Well, I need my second reactant and I need to measure it again. So for step 3, and I'm bullet pointing these like a recipe. So for step 3, I'm going to weigh 1 gram of magnesium. Of magnesium ribbon. Now if I put, no, it says accurate. Now if I put using a 2 decimal place balance, that's about as accurate as I can possibly afford to be. Okay. Then I'm going to add the magnesium and quickly replace the bung to stop gas escaping. I'm going to, so once all magnesium is reacted, record the volume of hydrogen gas collected in the syringe. Finally, and this is what's probably going to elevate it from a 5-mark answer to a 6-mark answer, is going to be repeat times 3 to ensure results are reproducible, or to assure a fair test, or to ensure reliability. You could add, make sure conditions are identical. Okay, right, I'm going to give you a few minutes to I'll put my written work up on the screen. You can kind of read it best I can. Okay, give you a couple of minutes. Ensure. Let's move that up a little bit. Doesn't make it much easier. Oh, that's not helpful. Going to give you another 30 seconds or so. You need to be quiet whilst everybody else is finishing. Okay, I think everybody's finished now. Anybody still writing, or we're okay? All right, let's go and do the next. So this is the last part of these. So last parts of question 7. Again, we have a graph. A graph is our friend. Yep, absolutely. It says calculate the gradient of the line on figure 14. Well, how do we calculate a gradient? We need to do y over x. So if I know the x, the figure for x, if I read that off there, is 6. Yeah. I'm going to use my ruler and a pencil, and I'm going to take that line back to the y-axis and read off the scale. Again, double checking the scale, exactly what each of those little boxes stands for. So that's going to be 4.8 divided by 6. Okay, 4.8 divided by 6, if you use your calculator, is going to give us, oops, I didn't need to do that, 0.8. Okay, now it's a 2-mark question. As I said before, you're getting 1 mark for writing that out. You get 1 mark for putting the answer in the right part of the paper. So just if your calculator stopped working and the batteries failed, you are still going to get marks on that question because you can write the 4.8 over 6. Okay, next. This is our last question. It says, determine the mass of copper that can be produced from 75 grams of copper oxide. Okay, there are several ways of doing this. The easiest is going to be using our graph. So, method 1, we go back to our graph using a ruler. Now it says 75 grams we're looking for. Now we can't do 75 grams of copper oxide because we've only got it going up to 6. But we could do 7.5 grams. We could scale it by a factor of 10, couldn't we? So we could do 7.5. So if we extend the line out here, extend that line, okay, and then, so we've extended the line out, so that's our first thing we're going to do, and then we're going to find out where 7.5 is on this axis. So again, making sure we're using our scale and making sure that we've understood what each one of those little squares symbolises, which is 0.2. So 1, 2, 3, 4, 5. That's going to give us 7. And then we need halfway between the 2 to give us 7.5. And I'm going to use my ruler to take that up and see where it intersects. And then across to that y-axis. So it's going to come out to about 6. Okay, so the mass for that is 6 grams, but we've already said we need to multiply by 10, don't we? Because we scaled it down by a factor of 10. So that's going to give us 60 grams. Okay, so our answer is 60 grams. Now that's one way of doing it. You could work it out mathematically using an equation, but I'm suspecting that the most obvious way, the easiest way, would be like that. Okay. It was 3 marks, that question. You will have got 1 mark for this scaling. You will have got 1 mark for finding the correct answer. That's 6, using the graph, extending the line, and that finding out that it's 6, and then one mark for actually realizing it's 60, not 6. Okay, the mark scheme itself Gives you a lot of different versions on how to do this, but you get 1 mark for realizing it's a factor of 10, 1 mark for using the graph correctly, and then 1 mark for getting a correct answer of 60. As I said, you could work it out using the gradient, or you could work it out using theoretical yield. But the easiest way is going to be that first one. Okay? Right. That's your complete paper. What I will say to you is, if you'd gone through there and if you'd done the paper and you had done any of it in pencil because you weren't sure, this would be your opportunity to go back through and use pen. It will also be your opportunity where you would read back through your answers to see if there's, just to double check them.